Hi everyone, my name is Yash. I go to Mission San Jose High School in Fremont.
My name is Alyssa. I go to Doherty Valley High School in San Ramon.
Hi, I'm Rohit. I'm a rising junior at Washington High School in Fremont.
Oh, hi, my name is Anirudh, and I'm a rising sophomore in American High School in Fremont.
And today we will be doing our colloquial presentation, which is about finding a cost-effective way to monitor pollution using drones. Next slide. Okay, so as stated before, what is our goal? Our goal is to design a proof of concept. Our goal is to design an unmanned aerial vehicle that can measure air pollution or So, what is an unmanned aerial vehicle? It is otherwise known as an UAV, and it is a drone or aircraft that can be controlled with a remote control or that can fly autonomously. Next slide. So, why UAVs? So, there's an overall trend across multiple industries of transitioning from human-centered processes to UAV-centered processes. Such as there are Amazon is now using drones to deliver, and it can also be seen with agriculture as well. And the advantages of using UAVs are that it's cost effective and it can be and its expanded sensing abilities. Next slide. So, how will we be using UAVs for pollution, for monitoring pollution? A UAV carrying pollution monitoring sensors can fly to multiple waypoints while repetitively gathering pollution and location data. This data can be sent back uh to us, and we can use that data to predict the potential pollution sources and monitor pollution trends.
So the problem with UAVs today that can detect pollution is that they're rather expensive. This is because the sensors that are used are expensive on their own, and there are additional costs that come with the weight of the sensors that can increase the cost of the frame. There are also the issue of repair costs, which also kind of exacerbates like the issue of the drone being expensive. However, we can cut that cost of the drone by almost about half if we're able to make it on our own with our own materials. These are the average costs of the parts that we would need to make our own pollution detection drone. So it might look a bit expensive, but this is far more cheap than the one that you could get on the market, but it can work just as effectively. The roadmap to achieve our goal is first to design and build an Arduino-based cost-effective pollution monitoring device. We will eventually use the UAV to collect data and demonstrate concept, or to make sure that this can actually work in the field.
Okay, so to measure the air quality with the drone, we have decided to look for four gases, which is nitrogen oxide, carbon monoxide, methane, and natural gas. So the reasons we select these specific gases is essentially because these are greenhouse gases and they're good indicators of climate or like pollution, right? Because they're horrible for the environment, and it's just a good indicator. So to measure these gases such as NO2, CO, methane, and natural gases, we're using an Arduino, which is paired with some sensors from DF Robot for nitrogen oxide and carbon monoxide, and a sensor from NCD for methane. The Arduino will store the data gathered by the sensors and will create a graph based on the outputs from the sensor. So like basically the main function of the drone is just to collect all the data up in the air and bring it back to the user, because right now we can't really transmit the data in real time, so we're relying on the drone to store it while it's up there and then bring it back down. Okay, on to the next slide. the features of the Arduino sensors. So essentially, when we get the sensors from the like factory or wherever we're buying them from, they're usually not calibrated. This means that the readings we're getting from these sensors can be really like inaccurate, right? And it's not exactly what we want. So first we need to calibrate the sensors, and then we need to test them in a controlled environment to make sure that they're actually accurate, right? So that we know that the readings we're getting once we actually put it on the drone are correct. And then after we do that, we'll test them in the real world and try to find whether or not our readings are accurate and the code works well. Next slide. Okay, so challenges during our development process. So the first was the incompatibility of hardware. So finding the cheapest hardware, but also making sure that it all worked together like well, because a lot of times many parts they don't like work well together, especially when we're trying to get it as cheap as possible. So first we had like failures, like propellers, motors, GPS, like a lot of things didn't match up, and we had to like end up reordering or like figuring out how to actually make them work together. And then the second thing was like, because like essentially this happened because they're all like not meant to work together. And instead of a lot of things being just plug and play, we had to use soldering because like a lot of times like it just doesn't work when it's just plug and play, and it's not going to work in a drone because it's in flight and has to be like more solid and rigid. And then the software tuning needed to be started from scratch because obviously this project isn't done a lot online, so we can't just use like code that's online. We have to actually just do it all from scratch. And then the third thing was there were a lot of like basically halfway through our project, some of the parts went missing, so we had to start from scratch and just do everything from the ground. Okay. Next slide. Yeah. Okay. So limitations of our design. First, cheap sensors mean that there's low accuracy of GPS and air quality data. So first off, the GPS sensor that we're using is we've consistently seen around like 5 meters of error during the testing, and this is just because it's a like cheaper GPS. If you want a more accurate GPS, then we're deviating from our end goal of having a cost-effective drone. So that is why we chose a pretty accurate GPS compared to like a really accurate GPS. So again, also electromagnetic interference from the like motors, it also makes the GPS accuracy worse. So yeah, like the odds are just against it, but yeah, we're just doing our best with what we have. And the second thing is air quality sensors that we're using can give fluctuating readings in different temperatures and humidities. So basically we can only get relative measurements and not exact measurements, right? We're not going to be like the measurements we get from these sensors is not going to be always like fully dependable. So that is why we're also implementing a humidity and temperature sensor into our drone. So this means that we can use the readings from the temperature and humidity sensor to kind of like figure out like the relation between the two, right? So we can figure out like how they're affecting each other. And this can help like kind of combat this like fluctuations in different of these sensors. And the third thing is there's low accuracy of data, which makes data analysis after we get the data a lot more difficult, because obviously if we see random spikes in data, it's kind of hard to tell if that's from the actual environment or if that's just from like the sensors itself.
Okay, on to limitations of our design continued. Secondly, flight time was very short. Our drone and battery are compact to maintain portability, but unfortunately, it comes at a cost. Currently, flight time averages only at around 10 minutes per change. Uh, this short window limits how far the drone can travel in a single flight and how much area it can cover before needing to return. Thirdly, we have no real-time data transmission. The drone's central flight controller has limited computational power and the radio link is constrained. We can only transmit basic telemetry in real time, like GPS coordinates, battery level, motor RPM, and internal temperature. We cannot stream detailed sensor data during flight, which makes real-time decision-making difficult. All other data has to be stored locally on the drone and then taken out and accessed only after the flight ends. Next slide. Okay. So now let's compare our project with the typical expensive commercial drone to highlight the trade-offs we're working with. Expensive drones, the pros are that these drones are designed for long flight durations, often 30 minutes or more. They offer high accurate data collection thanks to advanced sensors and processing systems. The hardware is reliable and the frame or chassis is durable enough to handle crashes or harsh conditions. The cons, however, is cost. These drones can run into thousands of dollars, making them impractical for widespread or disposable use. So the pros of our project include that they're very low cost, making it ideal for scaling or using in risky environments where loss is possible. However, the trade-offs include we deal with short flight times, which limits operational range. Our sensors aren't as precise, so data accuracy is limited. And because we're using lightweight and affordable materials, parts break more often, which increases maintenance. Okay, next slide. Um, so this is the work we've done so far and what we're working on and future goals. So done so far, we've basically created a pollution monitoring system using Arduino. And we're currently building a functional UAV capable of stable flight. And where the future goals include applying for UAV license, protocol for UAV ground control and pollution sensing to send commands to each other, uh, conduct multiple flight tests and analyze performance, and if performance is satisfactory, finalize proof of concept, develop a machine learning model to identify pollution patterns and improve sensor efficiency to tie all of these together and improve performance.
So, we'd love to give a special thanks to our research advisor, Dr. McMahon, and the ASDRP lab, and the All of Children Foundation.